In this video, we are going to continue with the graph of sine and cosine functions, and we're going to focus in on this third bullet point, sketch translations of the graphs of sine and cosine. And also the second one here, use amplitude and period to help sketch the graphs of sine and cosine functions. So the constant c in these general equations, we have y equals some number sine of some quantity b times x minus c, or the same thing for the cosine function. The variable c here is the horizontal translation or shift of the basic sine and cosine curves. So just real quick, if we have our xy axes, and here's our sine function. You know, as we put different numbers in here for c, plus or minus c, that's going to take our graph and it's going to shift it to the left or the right, back or forth. It's just going to take the graph and move it to the left or right. Let's see here. It says comparing y equals a sine bx with y equals a sine bx minus c. You'll find that the graph completes one cycle from bx minus c equals 0 to bx minus c equals 2 pi. By solving for x, we can find the interval for one cycle. You know, so here will be our left endpoint, and here is our right endpoint, and this is our period of the function. It looks kind of confusing now, but when we dive into an example, you'll see how clear this becomes. So, graphs of sine and cosine functions, we have the following characteristics. We know this number in front of the trig function, sine or cosine, its absolute value is the amplitude. We talked about that in the last video. That is how high the hills go and how deep the valleys go in the function. The period of the function, or how long it takes to complete one cycle, is going to be 2 pi divided by whatever number is in front of the x variable. If this was a sine 3x, we'd divide 2 pi by 3. If it's 1/2 x, we'd divide 2 pi by 1/2. And here's an easier way to look at what we saw in the previous slide. The left and right endpoints of one cycle interval can be determined by solving these equations. Bx minus c equals 0. You know, 0 is where the basic trig functions begin. Or bx minus c equals 2 pi. You know, the usual cycle is 2 pi. So those are the old endpoints, 0 and 2 pi. We take whatever is within these parentheses. Bx minus c, we set that equal to 0. We take the same value within the parentheses, bx minus c, and set it equal to 2 pi. Those will be the beginning and end points of one cycle of our graph. So here in example 4, it says analyze the graph of y equals 1/2 sine of the quantity x minus pi over 3. So analyze the graph. Well, the first thing here, we see the number in front of sine is 1/2, and that is our amplitude. Amplitude is 1/2. What is the period of this graph? Well, in front of the x here, we don't see a number, but we know there's an implied 1, and the easy way to find the period is take 2 pi and divide it by the number in front of x, and that's just a 1. 2 pi divided by 1 is 2 pi. This number here is our shift to the left or the right. So we're going to find our endpoints. You know, the basic sine function begins at 0 and ends at 2 pi. So we're going to take what is within those parentheses, x minus 1/3 pi, and we're going to set it equal to 0. And if we add 1/3 pi to each side, we'll get x equals 1/3 pi. The other endpoint is x minus 1/3 pi is equal to 2 pi. So again, if we add 1/3 pi to both sides, we're going to get x equals 2 1/3 pi. And let's start to put this information together in our graph. The amplitude is 1/2. So we know the peak of our hills will be at positive 1/2. The bottom of our valleys will be at negative 1/2. Now the sine function usually begins at 0 and ends at 2 pi. And you know, right in the middle between 0 and 2 pi is 1 pi. But now we have this shift. We've been shifted 1/3 pi. So our starting point isn't 0, it's now a third pi. So here's pi over 3. And then our end point is 2 and 1/3 pi. So right about here we'll put 2 1/3 pi. You know, we usually started at 0, we've been shifted to the right a third. We usually end at 2 pi, we've been shifted to the right a third. And remember, we want to chop our interval, our period, up into 4 equal chunks. If we did start at 0, we would add 1 pi to find our next x-intercept. And we can do that here. If this is 1/3 pi, we can add 1 to it and get 1 1/3 pi. 1 1/3 pi. So we know that sine starts on the x-axis. 2 pi later, it's going to end on the x-axis. And right in between there is going to be an x-intercept. So here's where we start, cross the x-intercept, and end our graph. In between these x-intercepts are our peaks and valleys. And that's going to come from adding a half pi to this number. Pi over 3 plus pi over 2, if we get a common denominator, it's going to be 2 pi over 6 plus 3 pi over 6. And if we add the numerators, we get 5/6 pi. That's a little bit less than 1. So this here is 5/6 pi, and that's going to be where our hill occurs, the top of our hill. And we do the same thing from 1 1/3 pi. We would add a pi to it, or we could go right from here. This is 5/6 pi. If we add a pi to that, we're going to get 1 5/6 right here below 2 pi. So this all come down lower is 1 5/6 pi. And let me get a little of this clutter out of the way. So we start here at a third pi, we go up to our first hill, down we cross the x-axis. We're going to come down here and we're going to have the bottom of our valley right about here. Actually, let me get this out of the way. So we have enough info to put our graph together. We start here at a third pi. Sine function, positive sine function is increasing. We hit our peak, and then we start heading down. We cross the x-axis at 1 1/3 pi. We come down here, bottom out at 1 5/6 pi, and then come back up to the x-axis. And if I do that in one continuous drawing, we can see here again this minus 1/3 pi. That's our shift. It shifted us to the right a third pi. If that was not part of our function, you know, our graph would just be slid over here. We would start at the origin, we would end at 2 pi, and would cross, well, that should be right at pi. But that minus 1/3 pi shifted us to the right a third pi radians. And there's our graph. Now let's take a look at another one here. Now we have sketched the graph of negative 3 cos of the quantity 2 pi x plus 4 pi. Wow, this one's a little more complicated than the last one, but we should be able to handle it. And let's see what we got here. In front of the cosine function is our amplitude, and remember the absolute value of that. So our amplitude is 3. So we know our top of our hills will go to 3, the bottom of our valleys will go to negative 3. The period, I'll write it here. To find the period, remember, divide 2 pi by the whatever is in front of x. In front of x here we have not just a number but also a pi symbol. 2 pi x. So we're going to divide 2 pi by 2 pi. And anything divided by itself is 1. So the period of this function is 1. And we also have this shift. Remember, we can find our endpoints. Where our graph begins is what is within these parentheses, 2 pi x plus 4 pi. 2 pi x plus 4 pi. First we set that equal to the original starting point, 0. And we'll subtract 4 pi from each side. 2 pi x equals negative 4 pi. And we can divide by pi, which will cancel those out. and then divide by 2. X equals negative 4 divided by 2 is negative 2. So that's where our graph begins. Our graph is going to end when we set the quantity within the parentheses, 2 pi x plus 4 pi, equal to the usual endpoint, 2 pi. So we're going to subtract 4 pi from each side. 2 pi minus 4 pi will be negative 2 pi, and that's equal to 2 pi x. Again, divide out the pi's, and divide by 2. X equals negative 2 divided by 2 is negative 1. So let's see here. Our graph begins at negative 2 and ends at negative 1. Well, if we come over here to the negative side, let's make this negative 2. About in the middle there will be negative 1. And let's even go on the positive side a bit. Positive 1, positive 2. And let's get some of this clutter out of the way now that we have our graph marked up. So, the period is 1. And we don't have, remember there are no pi now on the x-axis. Our period is just 1 radian, not 1 pi radians. So, we begin the cosine graph at negative 2. And usually cosine starts at the top of a hill. But this is negative cosine, and that's just a reflection around the x-axis. So instead of our cosine graph starting up here at the top of a hill, it's going to start at the bottom of a valley. And our graph begins at negative 2. 1 radian later, it's going to end at the bottom of another valley. In between those bottom of the valley is negative 3 halves, and that's going to be right below the top of our peak. And then at the quarters, negative 1 1/4 and negative 1 3/4 will be our x-intercepts. So if we start to draw this graph, we're going to start here at the bottom of the valley, come up real sharp, cross at negative 1 3/4, up to the top of the hill at negative 3 halves, and then come back down, cross the x-axis again, back down to the bottom of a valley. So we've done one full cycle. Up, peak, back down, finish where we started over the course of 1 radian. And just to do another example of it, let's graph the next cycle. From negative 1 to 0 will be another cycle, so we're going to end this graph down here at negative 3. In between here we have negative 1/2, and that's going to be the point below the top of our peak. And then we have our quarters, negative 3/4 and negative 1/4. And we go up, cross the x-axis, hit our peak, back down, and we end here on the y-axis at negative 3. And that pattern would continue. Something roughly like that. Now, a final type of transformation is a vertical translation caused by this variable. You know, I like to sort of tie this into y equals mx plus b. When we were graphing straight lines, this plus or minus b was our y-intercept. You know, if this was, let's say, 1x plus 0, it would go right through the origin. Oops, that was pretty bad drawing, but I can just move it down. Here would be 1x plus 0. This would be 1x plus 1, y-intercept of 1. 1x plus 2, intercept of 2. This d does the same thing. It's going to take our sine or cosine wave and just move it up or down in its entirety. So a rough sketch here. Let's do a quick sine wave, something like this. And let's say on our y-axis this is 1/2, 1, and up to 2. If I put a plus 1 in front of my function, that's just going to move the whole graph up 1. If it was 2 plus sine x, it would move it up to 2. So the shift is d units up if d is positive. It's d units down if d is negative. In other words, and I think this is the key right here, the graph oscillates around the horizontal line y equals d. You know, usually our graph oscillates around the x-axis. This number here is the new line around which our sine or cosine wave will oscillate. So here it says sketch the graph of 2 plus 3 cos of 2x. Well, let's see. Our amplitude, how much the graph goes up or down, is 3. The period is 2 pi divided by the number in front of the x variable. 2 pi divided by 2 is pi. So this function has a period of pi radians. This number 2 is the number or the line that we will have our graph oscillate around. Let's see here. I'll do this. So I got to make sure I get my scaling right here. Let's say this is 1, 2, 3. We got to go up to 5, 4. Extend this up a little bit. Here would be 5. Now this line here, y equals 2, is the line that our graph will oscillate around. So if I come here, nice thin red line. Usually the sine wave or cosine wave would go around the x-axis. That 2 has shifted us up 2, and we're going to go up and down around this red line. And let's do this. I'll use a couple blue lines here. From this red line, our amplitude is 3. So from this red line, we'll go up a maximum of 3, 1, 2, 3, up to a height of 5. So the highest our graph will go will be about this upper red line. And from this 2, we can go down 3. Down 1, down 2, we can go down here to -1. So I'll put another line here. Alright, we have the amplitude. We know we'll go from 5 to -1. The center of this graph, so to speak, will be the line y equals 2. And our period is 1 pi. So let's go right about here. We'll make pi radians. Here's a half pi. And then we'll have our quarters, 1/4 and 3/4. And let's see, it's a positive cosine function, so we're going to start at the top of a hill. You know, we would start at 3 if not for this 2. We're going to jump up to this peak. So here this cosine graph will start at 5. 1 pi later it will end at the same peak, height of 5. In between these peaks, halfway between, at a half pi radians, we will have the bottom of our valley right down here. And then at the quarter pi radians, we will cross our center line at y equals 2 here and here. So if we start to sketch in our curve, we start at our peak, head down, we cross our center line, y equals 2, down here to the bottom of the valley at y is -1, and then we start to bounce back up, cross our center line here, and then up and finish off our cycle. Not the best curve, but you get the idea. And so this number at the very beginning is going to be the shift up or down. If we did not have that 2 line there, this whole graph would just be moved down. Ooh, I should have made that one continuous line. So this +2 here, just move the whole graph up 2. If we didn't have it, we would have our amplitude of 3 from 3 to -3, and then our period would still be 1 pi. That +2 just took the whole thing up 1/2 units. And there we go. 3 problems for the huddle. Number 19, just describe the graphs F and G. Consider their amplitude, period, and shift. What's the same, what's different? In number 49 and 56, sketch a graph of the function, include 2 full periods. So pause the video here, try the huddle problems, come back and see how you did. Okay, for number 19, first let's consider the amplitude of both functions. The amplitude is the coefficient in front of the trig function. Here it's 1 sine of x, and we also have 1 sine of x minus pi. So the amplitude is the same for f of x and g of x, and it's equal to 1. The period. The period is 2 pi divided by the number in front of the x variable. Here we have a 1x, and in the function g of x we also have a 1x. So the period for both functions is 2 pi divided by 1, or 2 pi. It's the same for f of x and g of x. And finally, the shift. The shift is just given by this piece right here, that negative pi. If it's a negative answer, it's a shift to the right. If it's a positive pi, it's a shift to the left. So, g of x is f of x shifted pi to the right. Again, the graphs would be identical, but just the g of x would pick up the graph and move it to the right pi radians. Now we're going to do a little sketching. So let me draw some axes here. Right in the middle. So our first function is sine of quantity x minus pi over 2 radians. For this function, our amplitude, the number in front of the sine function, is 1. The period, 2 pi divided by the 1 in front of x, is 2 pi. And then we have this shift, negative pi over 2 radians. So our endpoints, our left endpoint is going to be x minus a half pi equal to 0, and solve for x. Add a half pi to each side. So a half pi is our beginning point. Our ending point is x minus a half pi is equal to 2 pi radians. Add a half pi to each side, we'll have x is 2.5 pi radians. So let's see, here's our usual endpoint, 2 pi. And then here in the middle we would have pi radians. I'll use blue for our new endpoints. So let's see here, our new starting point is not going to be at the origin but at a half pi. And our new endpoint will be at 2.5 pi, right about here. We usually have an x-intercept 1 pi away from the starting point, from 0 to pi radians, but now that's going to be a jump from here. A half pi, add 1 pi to it, we get 3 halves. And we should just about have enough to start our graph. So it is a sine wave, it's positive, so we're going to start at the x-axis and be heading uphill. We're going to start here at a half pi, we're going to end at 2.5 pi. Right in between them, smack dab in the middle, is our other x-intercept, 3.5 pi. In between these x-intercepts, we are going to have the peak of a hill. Let's put our 1 here, -1 here. So, our first hill, it's going to be at right above pi radians, up here at a height of 1. In between our next two intercepts will be a valley right in between, at the bottom of that valley, right at 2 pi radians. So, graph starts here, heads uphill, hits the peak, comes down, cross the x-axis, down into the valley, hit our low spot, come back up. And there we go, the graph of sine of x minus a half pi. Again, this half pi was a shift. It moved our graph to the right half pi units. You know, we usually start at 0, end at 2 pi, and have our x-intercept right about in the middle. So that minus a half pi radians just shifted us over. Boom. And 56. So let's see what we got going on here. Our amplitude is not 1 now. Our amplitude is 2. Let's see here, our period. In front of the x is a 1. 2 pi divided by 1 is 2 pi. And now here we have a shift. We're going to shift down, because it's negative, down 3 units. Shift down 3 units. So what I'm going to do here is move this x-axis up. So let's say here -1, -2, -3, -4, -5. The first thing I like to draw is the line our graph revolves around. We have shifted down 3. The graph usually goes around the x-axis. Now we're going to move down 3 units. So we're going to be, our graph will oscillate around this red line. And let's figure out our amplitude. From that red line, our amplitude is 2. So we can go up 2, 1, 2. So the highest our graph will go will be this blue line at -1 on the y-axis. And how low will it go? Well, from our shift down to 3, we can go down 2 more. Down 1, 2 to -5. So again, our graph is going to be wrapped around the red line, and it won't go higher than the blue line at -1 or lower than the blue line at -5. And our period was 2 pi, which is typical here. So let's do 2 pi. Cut that in half at a half pi, and then or at 1 pi, and then our half pi increments. And those are just our quadrant angles from the unit circle. Half pi, 1 pi, 3.5, 2 pi. So it's a positive cosine function. Positive cosine function starts at the top of a hill. It's going to start right here. At the end of the cycle, 2 pi later, it will be right back at the top of another hill. In between those peaks, right in the middle, will be a valley below pi. And then we will have x-intercepts in between the peaks and valley. In between this peak and valley, we'll have an intercept here on our center line at a half pi. And between this valley and peak, again at 3/2 pi. So positive cosine, we're on a hill and then we start going down. Cross our center line, come down to the bottom of our valley and head back up. Cross the center line again and back up to another peak. Ooh, and I did miss it on the last one. It does say include 2 full periods. Well, we have this period on the positive side of the y-axis. We could do the same thing on the negative side. Here would be -2 pi radians, -pi, -1/2 pi, and -3/2 pi. Again, we're here at a peak. 2 pi later, we would be at another peak. In between, we would have a valley down here below -pi, and then our intercepts at the halfway points. So right about here. And we could continue this graph, come down this way, cross down to our valley, cross our center line again, back up to another peak. So there are the 2 full cycles like we were supposed to show. But the amplitude was 2, and we were wrapped around a center line of -3. And in case you forgot your homework paper, here is a peek at the assignment for this section and day's work. Page 495, 16, 21, 22, 31, 34, 44, and 49. Enjoy.